Assalamu alaikum. I hope that everything goes in your side. Uh, Today we will continue our course. Is there any question from the last session? Okay. Okay. During the last session, we talked about datagram format of IP version 4 and IP addressing. And today we will continue our course, starting with NAT service. Suppose that we have a network with with a range of IP addresses and some systems, and we want to send information outside outside of my network to internet. To do this, I need some valid IP addresses. IP valid means that my IP address must be unique around the world in the internet. But in IP version 4, I know that there are not enough IP addresses for the all systems around the world. So we need to do something. To solve this problem, we need to move toward IP version 6. But before that, before moving toward IP version 6, one strategy is using NAT, or Network Address Translation. What is NAT? In NAT, inside the network, inside my network, I can use a range of IP addresses. But at the edge of network, in the edge router, I'm running NAT services. This service will translate my invalid IP addresses into valid IPs. I need to change these invalid IP addresses into a valid IP addresses. And NAT will do it. Again, a valid IP address is an IP address which is unique in the internet. It is not repeated over the internet. But inside my network, I can use different ranges of IP addresses inside my network. So maybe my address is very repeated somewhere else. So I said it's not valid. Okay, I said it's not valid. But if my address is not valid, what will happen? A valid IP address and invalid IP address, there is no difference between a valid IP address and invalid IP address. But if I use an invalid IP address over the internet, then the routers inside the network, inside core of internet, they cannot find correct path to my computer. Why? Because my address, my IP address is repeated somewhere else. I don't know where. Okay? I don't know where. But it's repeated somewhere else. So some packets may transfer my site, but their replies wouldn't receive to me because my address is invalid. It's repeated over the internet. So my packets may be goes toward another path, another destination. Why this happened? Because I have not enough IP version 4 addresses. There are some special ranges, spaces of IP addresses. I can use them freely, but the rest of IP addresses I should pay for them and buy some special ranges or spaces of IP addresses. Okay. For example, the private IP addresses are 10/8, 172.16/12, and 129.168/16 prefixes. There are 3 different spaces. In these three spaces are private IP address, which it means that I can use them and you can use them too. So they are not valid IP addresses. And I must not use them over the internet because they are repeated over the internet. I'm using them in my network, and at the edge of my network, the edge router would transfer these repeated IP addresses into a valid IP address or into a bunch of valid IP addresses. With this strategy, I can use one or a few valid IP addresses instead of using too many IP addresses for my network. For example, in the university, maybe we have 2,000 connected devices. So I need 2,000 IP addresses. But using that, only I need one valid IP address, not more. Okay? I can change IP addresses inside my network without notifying other world outside of my network. Why? Because I'm translating the addresses. And even the outside of my network, for example, my ISP can change its IP addresses without any effect on my internal network. And also, there are some security benefits too. Using that, I'm hiding this internal structure of my computer, my network. Why? Because I'm using my private IP addresses. So nobody can directly connect to my computers, inside my network. Nobody, because it's not private. So, but how a NAT service works? Let me pass this slide and touch on this slide here. Let's suppose that I'm using a private range of IP addresses with this one. For example, I'm using range of 10/8. For example, 10.0.0.1. I'm assigning this range, this address to this computer. And this computer decided to connect to a remote server. For example, this one. So it sends a packet. Look at these addresses. The source address is 10.0.0.1 with port number 3345, and destination is 128.119.40.186 with port number 80. Okay, my system sends this packet. It will receive to the edge router. In the edge router, I'm running NAT service. This service has a translation NAT translation table. The NAT service writes this information. 10.0.0.1 with port 3345 must be translated with 138.76.29.7 with port number 5001. The service writes this information in its table and changes my IP address. Look at this one. In packet 2, the source address has been changed. Source address and port number. And then this packet transfers over the internet. After a while, the reply will return. Okay? And you can see the source address and destination address. The destination address is 138.76.29.7 with port number 5001. Again, the NAT service will check its table and find that, okay, its address should be translated into this address. 10.0.0.1, port number 3345. And so, look at this one, packet number 4. You can see again the address and port numbers have been changed. And their primary values substituted. Put in the packet header. This is the behavior or the acts of NAT service. It translates my private IP address, my invalid IP address into a valid IP address and valid port number. And in return, again it replaces the valid IP address with my own IP address. Using this strategy, I can hide my internal network from the outside because I'm changing everything. Here, if you use Cisco devices, okay, or if you read Cisco documents, you can see two phrases, at and net. Two concepts, at and net. Let's see that together. Totally we call them nets, but Cisco says that, okay, if you change or translate a couple of invalid IP addresses into a couple of valid IP addresses. this path, Cisco says that if you translate a couple of invalid IP addresses into one valid IP address, only one IP address, Cisco calls it as PAT, or port address translation. Why? Because Cisco says that, okay, we changed all IP addresses into one IP address, but we have to use different port numbers. So we define different traffics only by checking their port numbers. Their IP addresses are same together, just their port numbers are different. So Cisco said, okay, this is PAT, not NAT. Okay, but here in this course, we always say no. This is NAT service. Okay. So we use NAT service. Why? Because the routers works on layer 3, and we see shortage in IP version 4 capacity. So we need to move toward IP version 6, but it needs time. This movement needs time. Okay. So one solution for this time, the time for migrating from IP version 4 to IP version 6. One proposed solution was NAT. But here, in today's in current networks, we use NAT strategy extensively. Why? Because of security considerations, especially security considerations. But for example, in our today's life, we see that cell phone standards and durations are parts of our lives. For example, 5G or 4G networks. They are telecommunication networks. Their structure is switching. Okay? But their backbone is packet switching. So we need to use NAT or something like that to connect those connected devices to cellular networks to connect to the internet. Okay, we use NATs in those big networks, but we know that the space of IP version 4 is limited because the length of IP version 4 is limited. Its length is 32-bit, but the length of IP version 6 is 128, 4 times differences. And someone says that, okay, if you use IP version 6, you can assign unique addresses to each molecule in the universe. Each molecule in the universe. Using IPv6 addresses. So we can solve the problem of address limitations for error by using IP version 6. But there are some other issues too, some other advantages or motivations to move toward IP version 6. For example, if you look on the header of IP version 4, you can see there are several fields in the header of IP version 4. The router must spend lots of processing power to process the information in those uh, fields, which is hard. So one another motivation in IP version 6 is that the scientists make the header of IP version 6 simpler than the header of IP version 4. And also, the header of IP version 6 is fixed, is 40-bit fixed. Also, they use the concept of flu for quality of service. What is a flu? Flu is a bunch of packets who are transferred in a specific path from a specific source to a specific destination. Okay, these packets are moving along a similar path with similar requirements. So we must process them similarly. Okay, so flow processing is another motivation happens in IP version 6. This is the header format of IP version 6. You can see this header is very simple, just 8 fields. You can see just 8 fields here. 2 of those are source and destination IP addresses, IPv6 addresses. Okay, just okay. Wait. Here, in comparison, this is the header of IP version 4, packet header of IP version 4. Look at this. Here you can see 12 different fields and an extra section for options. Maybe so your packet has some options, maybe have not. Maybe has or maybe has not. Okay, but primarily we have 12 different options, different fields: version, header length, type of service length, identifier, flag, fragmentation, offset, time to leave, upper layer, header checksum, source address, and destination address, plus an option part. Here you see it's very complicated. Very complicated. But in comparison, the header of IP version 6 is very simple. Very simple. It only needs 8 fields for calculation. The first one is version, which is 6, then priority, flu label, payload length, next header, and hop limit, and 2 addresses. Hop limit is similar to time to live in IP version 4. They are equals. Time to live or TTL in IP version 4 and hop limit in IP version 6. For the next header, payload length shows the length of payload. Here we have 2 other options, priority and flu label. Let's suppose that I have a packet with an important packet with higher priority, with the highest priority. Okay, how should I announce this priority? In IP version 4, we have nothing. But in IPv6, we have priority field. In priority field, I can identify that, okay, this packet is important for me. This packet is not. Okay? And a 3-byte full label. As I said, this full label is for quality of service. When a packet receives, I can check its flu label. It tells me that, okay, this packet belongs to, for example, follow X. Simply I can check the requirement of follow X. And according to that requirement, the router can determine the output path of the packet. Great. I don't need to process and to find the destination forwarding table and find the output port in the forwarding table. Just simply I check the full label and say, okay, this flow must go through the port, for example, number 6 with this requirement. Interesting. So this field is important for us. And also, as I said, when I'm checking the flu label, it shows me, okay, this flu label belongs to flu X and its requirements are something like this, blah, blah, blah. So I can grant it the quality of service requirement of the traffic simply because I know the requirements. Okay. In this format, we can say there is no checksum section, checksum field. There is no fragmentation and fragmentation offset, and there is no options. But how I can remove the options in IP version 6? We don't remove them, but simply we bring them to the payload part and the next header. Excuse me. The next header. What does it mean? I have 40 bytes of header, and if I have an option or something else, simply I can announce them as a next header. Here we have a field next header. It's a pointer to the content in the payload. Why we call it next header? For example, in IPv6, I can use IPsec inside in the heart of IPv6. In IPv4, if I need IPsec, I should run it in a different computer as a different service. But in IPv6, I can run IPsec inside the heart of IPv6. But how? I'm adding a new header for IPsec here in the payload part. Okay? So, but why we call them next header? You know, for example, if I use IPsec, just a few routers inside the path toward the destination. Just a few routers needs to check this header. So next header means that I'm adding those information into my packet, but if one router decided to check it, it can check. But if does not need to check it, it doesn't check. Simply. Okay? So we put every other things into the payload part, and now I know that the header, the length of IPv6 header is fixed to 40 bytes. It's very good. By this modification, removing checksum, removing fragmentation, removing options, make it simple, we know that we can save too many power processings and processing times in routers, especially in core routers. That is great. But one main question. Okay. We start to move toward IPv6 from 25 years ago, 1995, something like that. Okay? But after this long time, after 25 years, still we have islands of IPv4 and islands of IPv6. Why? Because we cannot put pressure on people. Okay, you have to change your old devices with new ones and use IPv4. I cannot do this. I cannot make force on people around the world. And also, some administrations, some managers says that okay, there are some management considerations, security considerations in IPv4. We cannot accept them at this time. Okay, so the world moves very slowly toward IPv6, even after 25 years. So the question is this: okay, I'm sending an IPv4 packet, for example, or IPv6 packets, but during the past, sometimes during the past, it must move inside an IPv4 network. It was passive. Okay? But the packet is IP version 6. What should I do? How can I transfer an IP version 6 packets over an IP version 4 network? How? There are some solutions for this. One of the main solutions is using tunneling. In tunneling, I'm putting one packet into another packet. Okay, I'm sending an IPv6 packet, but it has to move, it has to pass across an IP version 4 network. So at the edge of that network, I'm creating a tunnel. I'm putting my IP version 6 IP packet inside IP version 4 packet. We call it tunneling. You can see it here. This is tunneling. The blue packet is IP version 6 datagram, and the red one, the pink one, is IP version 4 packets. You can see the IP version 6 is placed in the heart of IP version 4 datagram. Especially in 4G or 5G cellular networks, we are using tunneling strategy. Look at this one here. For example, system A wants to transfer a packet to some packets to system F. Both of them are IP version 6, but those packets should be passed this cloud of IP version 4. So in this network, we have to use tunneling strategy. We have to encapsulate all IPv6 packets into an IP version 4 packets. Okay? And here you can see this tunneling is happened between B and E. So B and E must knows everything about IP version 4 and IP version 6 to create that tunnel. Here you can see my packet from A is sent to B, and B creates a tunnel. It put my packets, it encapsulates my packets into an IP version 4 packet. Then this packet has been sent over the network into the other end of tunnel, and in E we can see packet, the main packet, the IP version 6 packet is extracted and it forwards through system E into system E. Okay, this is a tunneling strategy. We have another strategy too, which is we call it dual stack. In dual stack, here in tunneling strategy, you can see that during the passing the IP version 4 network, I'm putting one packet inside another packet. So I'm making some overheads. I'm adding some overheads to my network because of tunneling. In dual stack, instead of putting one packet into another packet, I'm changing the header of packet. I'm translating the header of IP packet version 6 into IP version 4 packet header. So completely I'm replacing the header from version 6 to version 4. And in the other side, again, completely I'm translating the IP version 4 header into a header of IP version 6. However, in this case, we lost full ID because the full ID in IP version 6 is appeared in IP version 6, but there is no space for full label in IP version 4. So we lost it. We lost the full label of IP version 6 if we use dual stack strategy. But it's another strategy without any other overheads. The tunneling, as you can see here, the tunneling has its overhead. This chart has some interesting statistics about the movement toward IPv6 all around the world. For example, the Google says that, okay, only 30% of clients who are connected to the Google servers are using IP version 6. Only 30%. Look at this. This book has been written on 2020. And at this time, Google says, okay, only 30% of clients using IP version 6 to connect to my servers. Interesting. And NIST, it's a big organization. NIST says that only 1/3 of US government domains are IP version 6 capable. In the chart, you can see that during a period of 10 years, from January 2010 to January 2020, you can see a movement, a fast movement to accept IP version 6 in the life of people. But as he said, only 1/3 of people in the world are using IP version 6. It means that this information, this statistics means that, okay, we need more times, too many times, to complete this migration moving from IP version 4 to IP version 6. We need too many times, at least 5 or 10 more years, at least. Okay? But why? I said, because we cannot make force on people to change their own devices, or we cannot some managers, some administrations says that, okay, there are some management and or security issues on IP version 6. So it's a slow but continuous movement toward IP version 6. And I think we need more 10 years to complete this path. But what we should do at this time, for example, if you look for strategies, for example, Microsoft presents a new tiling strategy for its application for moving IP version 6 toward the destination across IP version 4 computer networks, or we can see some other changes in the application world during these 25 years. Okay, so some application level changes helps us to tolerate this slow movement toward IP version 6. Okay, that is enough for today. Any question? Okay, thank you for joining the class. Have a good day and